So we're starting a new chapter. We're going to be using, it's called applications of derivatives, so we're going to be using derivatives to do things. And the first topic that we're going to discuss is called related rates. Okay, so what are related rates? Well, they are things that are related. So let's draw a picture to give you an idea of what we're talking about. Let's go into writing mode. So let's say that you have a balloon. Actually, let's use the thing to draw a circle. Here's your beautiful balloon. And it has a radius. Boom. Oh, that's like perfect. Okay, it has a radius. Now, let's say that you have a pump. So there's like your little hose. And here's your little pump. So, there's like those floor pumps. You like pump it up and down. Now, let's say that you have a rate at which you pump air. So there's a rate at which you pump air. Okay. So remember, you measure air as a volume. So what you could say is like, hey, I don't know, the air is going in at a rate of 5 liters per minute or something like that. Is a liter a measure of volume? I want to say a liter is a measure of volume. Am I right about that? I guess we could always use cubic inches. So you use like 25 cubic inches per minute. But I think liters are a measure of volume. If I'm wrong, then my bad. I'm in America. Yes, thank God. Yes, liters are a measure of volume. Thank you for a person who made me feel more confident in the chat. Okay, so you're pumping air in at some rate. Now, what is going to happen to your spherical balloon as you pump more air in? Like, what's going to happen to the shape of that object? Yeah, exactly. So let's draw our bigger balloon. Let's make it bigger than that. There we go. Our balloon has ballooned. I made a joke. Okay, so let's draw in the new radius. Cool. So you went from that radius to that radius. So there's the rate of change at which you pump the air. Now what's going to be really interesting is that there's going to be another rate. The rate at which the radius is increasing. Increasing. That's what we mean by there are related rates, because the rate at which the radius is increasing is connected to the rate at which you pump air. There's a connection there. That's what we mean by they are related rates. If you pump in air at a higher rate, the radius will increase at a higher rate as well. Does that make sense? If you pump real slowly, the balloon is going to expand real slowly. If you pump real quickly, the balloon is going to expand real quickly, relatively speaking. Okay? So, what does this have to do with derivatives? Well, you can remember that derivatives are used to find instantaneous rates of change. So, the rate at which you pump in air is a change of volume. We would say that dV dt, the rate of change of volume with respect to time, is 5 liters per minute. Now, how do you figure out the appropriate units? It actually helps you to look at the derivative. If you look at the derivative, do you see how it's V on top and V is volume? And what can you measure volume in? Liters. Liters are a measurement of volume. And then you look on the bottom, T stands for time, and if you look at minutes are a measurement of time. So do you see how that's how I know it's dV dt? Because it's liters per minute, like the units will match. Likewise, if you go to the other one, we're talking about the radius increasing. So that's dr dt. R is the measure of the radius. T is a measure of time. So your radius might increase at 1 centimeter per second. Why? Because the radius is a unit of length. You would measure that in centimeters. Time is seconds are a measurement of time. dr dt would be like centimeters per second. dV dt would be liters per minute. But the whole idea here is that this derivative, dr dt, is going to be somehow related to this derivative over here, dV dt. When you come up with an equation that relates those two derivatives, what you are now doing is a related rates problem. Oh, thank you for the person who Googled that liters are a measurement of volume for me. Thank you. I didn't want to take a moment to do it. But hopefully you see what I'm talking about here. That you have one change and that's affecting some other change, and we want to know the connection between the two of them. Okay, so let's do a quick example here, and I'll show you what's going to be going on here. So you need to relate volume and the radius. We have dV dt and dr dt, which means we need an equation which relates the radius and the volume. And remember how I said that the balloon was a sphere? So does anyone know the equation which relates the volume of the sphere to the radius of the sphere? Do you remember? What is the equation which relates the volume and the radius of the sphere? Yeah, the volume is 4/3 pi r cubed, and it's cubed, not squared, because volume is cubic inches, right? Square would be a measure of area, so good catch there. When I noticed you caught yourself. You must have thought, wait, no, it'd be cubic. Okay, now, see, this equation relates volume and radius, but we're working with their rates. We want to relate their derivatives. So how will you find their derivatives? Well, you're going to take the derivative of everything with respect to t. So first you're going to have to find an equation which relates the two values that you want, and then you're going to take its derivative. So on the left-hand side, you're going to end up with dV dt. That's one of the things that you wanted. Now on the right-hand side, you're taking the derivative with respect to t of 4/3 pi r cubed. You can factor out those 4/3 in the pi. And what you can use now is implicit differentiation, because you're taking the derivative with respect to t of r. The variables don't match. So what I want to point out here is that to solve these problems, one must often take the implicit derivative, since the variables do not align. What do I mean by they don't align? I mean, we're taking the derivative with respect to t of r. And we're like on the left, we're taking the derivative with respect to t of v. So on the left, we have our dV dt. On the right, we have our 4/3 pi. Okay, now if you take the derivative of r cubed, that's going to give you 3r squared. And then you have to multiply by dr dt. That's what the implicit derivative tells you. Okay, now notice you have an equation which relates dV dt and dr dt. this is what you'll have to do to solve these sorts of problems. I haven't done a complete example yet, but I'm just sort of showing you vaguely how the process is going to go. You're going to find an equation which relates the two variables you want. Then you're going to have to take the derivative to get the derivatives or rates of change that are related. And let's simplify here. Notice that this 3 on bottom and this 3 right there is going to cancel. So this whole thing is going to tell you that how is the change in volume related to the change in radius? Well, dv dt, which is the change in volume, is going to be equal to 4 pi r squared times dr dt. So if you know dr dt, the rate at which the radius is expanding, multiply that by 4 pi r squared, and then that will give you how the volume is expanding. So this one is rate of change of radius. What is this one over here? Rate of change of volume. Doesn't matter which one you solve for. Usually you want to solve for the one that you need to that you want to find. So if you wanted to find the rate of change of the radius because you knew the rate of change of the volume, you would solve for dr dt. This would be useful if you knew how the radius was changing and you wanted to figure out how quickly the air was being pumped in. Okay, so we'll go through and I'll show you how to do a full problem, but I want you to think about it conceptually first. You want to figure out how, if this is what this rate is, if this is how quickly I'm pumping in the air, I want to know how quickly the radius will be changing. Or let's say I want to know, or let's say I know how the radius is changing, or sorry, I know how the volume is changing, I want to know how the radius is changing. Or if I know how the radius is changing, I want to know how the volume is changing. Okay, that's what we mean by related rates. The process to actually do this, however, involves finding an equation which relates those two variables, taking the implicit derivative, and then getting an equation like this.